Hey everyone, and welcome to this third lecture in the series of the topic sequences and series. In the first two lectures we looked at arithmetic series, basically focusing on arithmetic progression. Then we followed that with arithmetic means, and now we're going to continue that with geometric sequences. So what we learned in arithmetic sequences is that if you have some list of numbers and if the relation between those list of numbers can be found out through addition or subtraction of a particular number, then that would be known as an arithmetic progression. So in the geometric sequence, that's a bit difficult. I will explain to you what geometric sequence is by the help of an example. So let's just say you get a job and your salary is $100 per week, and it is stated that every week your salary is going to double. What would your salary be after 4 weeks? Now the easier way to find out is that you write 100, then you write 200, 300 and 100 and 200, and then 400, 800, 600, like that, so on and so forth. So as you see that these values that you have over here, these $100 for the first week, $200 for the second, then you double this and then you get 400, then you double that, you get 800, and then you double that, you get 1600. These values form a geometric sequence. One thing to note particularly in this example is that none of these sequences are connected to each other by the help of a subtraction or addition of any number. I mean, for example, if you look at the second and the first term, if you subtract the second and the first term, just the way we used to find the common difference in a arithmetic sequence, you would get 100. But if you subtract the third term from the second term, you're not going to get 100, you're going to get 200. And then the fourth term, 800 from the third term, you're going to get 400. So that basically tells you that this is not an arithmetic progression. Why? Because it does not have a common difference, and since it does not have a common difference, you cannot form an arithmetic progression out of this. So this will be called a geometric sequence. Now this is just one of the ways how we can see it. Of course, there are many other properties of geometric sequences that we're going to look through, and there are many other things that we need to see for us to call it a geometric sequence. One of those things that we are going to concentrate on, basically that is how we know that this is geometric sequences, that is the difference between the arithmetic progression and the geometric sequence as well, and that is in the arithmetic progression we had a common difference. In a geometric sequence we have a common ratio. So this is how you can define a geometric sequence: a sequence in which each term after the first is found by multiplying the previous term by a constant value called the common ratio. Now it is not saying that it's going to be multiplied by a particular number, because if you are going to do that, that means you're going to multiply 100 by 2, then 100 by 4, 100 by 8. It doesn't work like that. You have to multiply. Over here, if you see the common ratio in this particular example, you can see that the common ratio is basically 2. So if you take the first term 100, if you multiply it by 2, you get 200. Then you take the second number, you multiply it by 2, you get 400. Third number, you multiply by 2, you get 800, and then 1600. So this is how we know that since it is being multiplied, since the next term is found by multiplying the previous term, we can call it a geometric sequence if there's a common ratio between terms, just like there was a common difference in arithmetic progression. Now let's look at another example. Find the first 5 terms of the geometric sequence with a1 is equal to -3. a1 is just like a we talked about in the arithmetic progression. That is, we have a1 is equal to -3, which is the first term in the sequence, and the common ratio is 5. So how do we find the first 5 terms? We multiply -3 by 5, that is the common ratio. Then the third term, we don't have to multiply the first term once again by 5. Of course, that would just give us -15 again, and then we can't find the values. We multiply the second term by -5. After multiplying the second term by -5, we get the third term. We multiply the third term by 5, sorry, we get the fourth term, and so on and so forth. This is how we find a geometric sequence. Now, find the common ratio of the sequence 2, -4, 18, -16, 32. Now this is a really simple question, and I'm pretty sure that you're going to get something of this type in an exam. Now if you look at the ratio, if you look at the series in front of you, you might get confused because there's a positive number and there's a negative number, then there's another positive number, there's another negative number, then another positive number. So how do we find the common ratio? The simple answer is that to find the common ratio, we divide any term by the previous term. Just like in an arithmetic progression, we used to find out the common difference by subtracting the third term from the second term, the fourth term from the third term, basically subtracting any term from the previous term, we got the common ratio. In this case, we're gonna get the common ratio by dividing basically one term from its previous term. That is, 8 would be divided by -4, so we're going to get a common ratio of -2. Let's divide the fourth term by the third term. -16 being divided by 8, we're going to get -2 once again. The fifth term, 32 divided by -16, we're going to get -2 once again. So this is how we basically find out the common ratio between a term in a geometric sequence. Now moving on. Just like arithmetic sequences, there is a formula for finding any given term in a geometric sequence. Now we're going to figure it out using an example, just like we did for the arithmetic sequence, arithmetic series in a arithmetic progression. We found out, we derived the formula by I just give you the formula for you to learn it right there and then. We basically derive the formula so that you can conceptualize it as well and understand it as well. So the previous first example that we saw, the first term is going to be $100, just like the salary example that we saw. After looking at $100, we get the fifth term by multiplying it by 2 to the power of 4. That we're going to get 1600. This is exactly like the salary example that we saw. So A5 is the term that we're looking for. That is the fifth term of the series. 100, as we know, is the first term. 2 is our ratio, and the n-1 is negative. That is, n is the fifth term, so n-1 is going to be 4. So moving on, we look at how do we derive the formula. Now just look at the this term over here. A5 is equal to 100 into 2 to the power of 4. It will give you the fifth term. So what do we get as a formula? So the way we get this fifth term is that a to the power an, that is a particular term, is basically equals to a, that is the first term, multiplied with the common ratio to the power of n-1. So if that is exactly what this is over here. If you have a to the power of n, that is the nth term that you need to find, the 7th or the 8th or the 9th or the 100th. What you do is you find out the first term that we had 100 with us. You either, if you want to know this one over here, you would already know the ratio. Once you know the ratio, you raise to the power of n-1, n being the term that you need to find. So find the 10th term of the geometric sequence with a1 is equals to 2000 and the common ratio of 1/2. So this is really straightforward. This is just, you need to plug in the values and you can get the answer. So a 10th is going to be a1, that is the first term, which is of course 2000. Common ratio 1/2, and n-1 is going to be 10-1. That is, there you're going to get 9 for this. You plug in the values, you move stuff around, you get the calculations. So this is what you're going to get. You plug in the values over here. 2000 multiplied by 1/512, 2 to the power of 9 is 512. You multiply 2000 with this, and then you simplify, then you simplify it further and then further, and find the next two terms in the sequence of -64, -16, -4. Now what I want you to do is you solve this question yourself. What do we know about this series and or the list over here? What we know about this sequence over here is that one thing that we already know, and it's not a trick question, is that this is a geometric sequence. So we know it's going to have a common ratio. How do we find that common ratio out? We divide the second term from the first term. -16 by 64 is going to give us 1/4, positive 1/4. Then in order to confirm that, we divide the third term from the second term, -4 being divided by -16. This is once again going to give us 1/4. Once that is done as well, what do we get after that? We get basically a common ratio of 1/4. So in order to find out the next term after -4, we basically multiply this term -4, the third term, by 1/4, and we're going to get what? We're going to get 1. 1 is going to be the fourth term, and then that's going to be a positive term, of course, because the ratio is not -1/4, it's 1/4. And then you move forward from that and you get the next number after that, that is 1 multiplied by 1/4. So that you're going to get 1/4 after that as the fifth term in the sequence. So this is done over here. This is explained, just the thing that I explained to you over here. So you just need to fill out these blanks. So this blank is of course going to be -1. Why? Because 1/4 is being multiplied by -4. And the blank after that is going to give you minus 1 by 4, because minus 1 will be multiplied by 1 by 4. So this is what a geometric series is. Now after we saw what a geometric series is, what do we see? What did we do in arithmetic progression? We went through the arithmetic means. So just like with arithmetic sequences, the missing terms between two non-consecutive terms in a geometric sequence are called geometric means. We saw that the missing terms between two non-sequence arithmetic terms terms in the arithmetic progression were called arithmetic means. Over here they're called geometric means. So we're going to go through the geometric means now. So this is what basically it means. If you look at the first thing, that the geometric means between 3 and 768 are 12, 48, 192. Two things you need to make note of over here. One thing is the number of geometric means between these two numbers. That is, there are three altogether. Altogether there are three geometric means between 3 and 768. After you're done with that, you need to find out, of course, like through in this question that we have over here, that they find two geometric means between -5 and 625. So I mean, what we did with the arithmetic progression was something similar to this. The only difference between this question and that question was that we used a different formula. Now we know what our unknowns are over here. So moving on with this example, this is what was the first thing that we need to write. This is the same thing that I told you for the arithmetic progression as well, that we need to write down the values so that we can visualize our answer. We need to know the common ratio. Of course, this is the first thing that we need to know. Since we only know non-consecutive terms, we'll have to use a formula and work backwards. Which formula are we talking about? The formula that we just derived, that is a r to the power of n minus 1. That is a formula that we are going to use for this. Remember that in questions like these, the best way to start this is that you write down these numbers so that you can visualize the things that you're going to solve. So we have 625 is the fourth term, -5 is the first term. We need to find out the third term, right? So in order to find out we know the fourth term over here. So first thing that we need to do is we need to find out the ratio. What do we have in the formula? We have an is equals to a to the multiplied by r to the power of n minus 1. We know this, and after we know this, what we need to find out after this is that is the ratio. So we plug in the values. 625 is the fourth term, -5 is a, and ratio is what we need to find, and n minus 1 is going to be 4 minus 1 because n is equals to 4. So 4 minus 1 will give us 3, and -125 is equals to r cube. Now the only way is we take the cube root of this and we get the ratio, and the ratio is going to be -125. Sorry, the ratio is going to be cube root of -125. That is going to give us -5. So we have, now we just need to multiply -5 to find the means. Of course, I mean, the first thing we need to do is we find the second one. We multiply -5. Remember, the ratio could be negative or positive. So don't get this wrong if you find a negative ratio, right? Over here you might make a mistake that you get a -5 ratio and you start multiplying it by 5. That's going to give you a different answer. For the second term, let's just say in this example, you multiply -5 by -5, you get 25. On the other hand, if you multiply with -5 by 5, you're going to get -25, but that will be the wrong answer. So the correct answer in this scenario is going to be -5 being multiplied by -5, we're going to get 25, and for the third term we multiply -5 once again with the second term and we get -125. So this is what it is. So what we did over here is we talked about geometric means. We have already talked about arithmetic progression and arithmetic series and arithmetic means. In this lecture we talked about geometric series and sequences, how to find different terms, and how to find geometric means. We're going to continue with this lecture on sequence and series. We still have some stuff to cover in geometric means. We have to cover the geometric sums, and that's going to be pretty interesting as well. This is how we do these questions. Just remember the formula, remember to visualize, and most importantly remember that negative and positive both can be the geometric ratios between two consecutive terms. So don't panic if you have a negative ratio, or even a ratio in fraction, or if you see a negative and a positive, both of these inside a geometric series. So thank you very much. That's pretty much it for this lecture, and hopefully I'll see you again. Bye.